Okay, we're almost in a position to define the main object of the first 2/3 of this course, the fundamental group. So let's now fix X topological space as usual, and we'll fix a base point x0 in X. So this is a point. We'll call it the base point. And we'll see that things do depend on the base point, but we'll understand the dependence as we go along the way. So here's the space. Maybe it's again a 2-hole torus, and here's the point x0. Okay, so now we're going to look at omega of x0 is what we previously called omega of x0. Okay, that is, it's just looking at paths alpha from 0, 1 to x, with both alpha of 0 and alpha of 1 being the base point x0. Okay, and as mentioned earlier, we have star and also alpha to alpha bar are defined on omega of x0, and we also defined already a set, but I'll call this way, pi1 of x0, and this is going to be the fundamental group, is omega of x0 by an equivalence relation, and equivalence relation is homotopy, fixing endpoints as usual. We had previously defined this equivalence relation. So there is only one piece that we need to have for technical nature to define this. So as I said, this is defined. There's nothing further to say. But we want to define operations on this. We want to show that the operations are well defined. So we have defined the operation star and bar on omega. What we need is that they're actually defined on the quotient. So for that we need things to be well defined. And indeed they are. I'll state this in a more general sense. So suppose we have alpha 1 is homotopic to alpha 2, fixing endpoints, and beta 1 is homotopic to beta 2, again fixing endpoints. Okay, and suppose we know that alpha 1 star alpha 2 is defined. So that means that alpha 1 of alpha 2 of 0 is alpha 1 of 1. So we can define these two. Okay, so then what we claim is that alpha 2 star beta 2 is homotopic to alpha 1 star beta 1. Oh, I'm sorry, here I need alpha 1 star, not beta 1, but alpha 1 star. Okay, let's correct this. Alpha 1 is homotopic to alpha 2. What we need is alpha 1 star beta 1 is defined. That is, alpha 1 of 1 is the same as beta 1 of 0. Okay, so then if I look at alpha 2 star beta 2, it is defined and it's homotopic to this, and also alpha 1 bar is homotopic to alpha 2 bar. That is, homotopy is compatible with both multiplication and inversion. Okay, and the proofs are really easy. So namely, if I just scribble them here, or rather draw a picture. So suppose I have H, so I want a homotopy between alpha 1 and beta alpha 2. So let's call that H alpha. Suppose I have H alpha with alpha 1 and alpha 2, and then I have H beta, and this goes from beta 1 to beta 2. Then I look at this box here where I have alpha 1 and I have alpha 2 above, and then I have beta 1 and beta 2 above, and I have H alpha and H beta. We did many more complicated things. This is what is A, and B I'll say easier even. Okay, B easier, I just say flip not in the vertical direction but horizontally. Namely, I look at H alpha, let me call it hat of ST. I'm not putting bar because that was a vertical flip, so that is H alpha of 1 minus S and T, flip in the S direction. So what this tells you is that the operation star and bar are compatible with homotopy, and that will immediately let you define thus we have induced operations. So first of all, we have a multiplication from pi1 of x x0 cross pi1 of x x0 to pi1 of x x0, and this is given by equivalence class of alpha, and equivalence class of beta gets mapped to equivalence class of alpha star beta. So the point of the previous result is if I have any other element, suppose this was equal to equivalence class of say alpha 1, and if this was equal to equivalence class of beta 1, then this would be equal to equivalence class of alpha 1 star beta 1, because we just showed that alpha 1 star beta 1 is homotopic to alpha star beta, and hence their equivalence classes are the same. And we also have operations from pi 1 of x x0 to pi 1 of x x0, which will take the equivalence class of alpha to the equivalence class of its bar. And again, if I had a different element with the same equivalence class, I would get equivalent elements here. So I have well-defined operations, and theorem is pi 1 of x x0 with these operations. Is a group. Okay, so here's of course a proof. Okay, what do we have to show? Well, we have a well-defined operation. Star is associative. Well, why is this? This is because if I look at alpha star beta and multiply it with the class of gamma, okay, this is homotopy class by a definition of the guy alpha star beta star gamma. You just apply the definition twice, but this is the same as homotopy class of alpha star beta star gamma, and that is because as alpha star beta star gamma is homotopic to alpha star beta star gamma. This is what we did the work proving. So now that we have done the work proving, we get this. We also get useful results in a couple of other cases, but that's the main application of this. And similarly, what we have is alpha star alpha bar. Oh, I need an identity before I talk of inverses. So if I let E being the class of E x0, then E star alpha is equal to alpha star E, which is alpha itself, and that is again because E star alpha is the equivalence class of E star alpha, and since homotopic curves give you the same equivalence class, you get the result that this is just the class of alpha, and the same there. And finally, if I look at alpha star class of this star alpha bar, I get E, which is also the other inverse alpha bar star alpha. So we get a group operation once we quotient by homotopy. Okay, I emphasize if we did not quotient by homotopy, you would not even get an associative product. E would not be the identity. There are less drastic ways of making things into groups, but you have to do something. Okay, and you can just consider a larger structure involving the homotopy, but one way or the other, you get nowhere without the homotopy. Okay. So this is wonderful. We finally have a group. We call this the fundamental group. Okay, and let's just, before we go to the functoriality, we'll just take one example. So let me just emphasize pi 1 of x x0 is called the fundamental group. It's not the fundamental group of the space X. That would not be correct. It's correct to say it's fundamental group of X with a base point x0, because it will depend on the base point. So this is the key term, fundamental group of X x0. So let me just take one quick example. Suppose X contained in, let's say, Rn is convex. Then we have the following proposition. Okay, so suppose I take alpha, beta are paths, so 0, 1 to x. Okay, then alpha is homotopic to beta if and only if the endpoints coincide. Alpha of 0 equals beta of 0 and alpha of 1 equals beta of 1. Okay, so proof, first of all, one way is true for all spaces. Okay, if alpha is homotopic to beta and H is a homotopy. Okay, so as remember, what was one of the conditions of a homotopy? The endpoints, it's a homotopy fixing endpoint. These are constant functions. So as T mapping to H of 0, S is 0 and T is constant, then we have alpha of 0, which is H of 0, 0, because we have alpha below, and we have beta above. Okay, is the same as H of 0, 1, but that is beta of 0. Okay, similarly, we have alpha of 1 is beta of 1. This is a general fact we'll use later also, that one way. I could have stated it as a separate proposition, but we'll state it later as a separate proposition and recall this proof. But how about the converse? What if I have two paths with the same endpoints? Well, I can just take convex linear combinations of this. Okay, so conversely, if alpha of 0 is beta of 0 and alpha of 1 is beta of 1. So, okay, so you define H of S comma T as going to be, we'll take the appropriate linear combination. So we'll take 1 minus T times alpha of S plus T times beta of S. So when S is 0, this is going to be alpha of S. When S is 1, this is going to be beta of S. And crucially, you look at, if we look at the function T mapping to H of 0T, the other function is similar, equals is T mapping to 1 minus T times alpha of 0 plus T times beta of 0. But we have assumed beta of 0 is alpha of 0. So this is going to be just alpha of 0. So this is constant. So the hypothesis that the endpoints were fixed made this a homotopy fixing endpoints. Otherwise you always get a homotopy. It's well defined, there's no problem. It's just that, so if I had one path here and one path here, I could just get a homotopy between them. It's just not a homotopy fixing endpoints. So, and where did we use convexity? If the set was not convex, this formula will not lie. This formula will not give you a point inside X if it took an arbitrary subset of Rn. Of course, if it was an arbitrary topological space, this is even completely meaningless. Okay, so we have the fundamental group, and so corollary from this is that pi 1 of x0 is just identity. Why is that? Because any two loops at the base point x0 have the same, both endpoints the same, namely x0. And so they are homotopic to each other. Hence there is only one point in this set. So this is a group with only one element, and hence it's the trivial group. So what we have is, we have a definition of fundamental group. We see it's well defined, and we can compute it in some cases at least, namely some cases where the fundamental group is trivial. The subject will take off when we, in the next set of videos, where we'll do the very interesting but certain amount of work in showing what the fundamental group of a circle is. Okay, using a beautiful covering space argument. That is the crux of the matter. But for now, we have the fundamental group defined.